Our next topic is finding the absolute maximum minimum of the function over closed bounded regions, like circular regions or rectangular regions, triangular regions, and so on. So the process is you need to find all interior points. You're basically finding the critical values by finding the partial derivatives with respect to x, with respect to y, and then finding the z values. Then you move on to the boundary points. It means that you look at the boundaries and start analyzing the function, reducing the function into one variable function, f of x, f of y, and find the minimum and maximum. After comparing these values, you can decide on the minimum, maximum of the function. Let us explain this using an example. In this question, we have x squared minus 2xy plus 2y, which is a function. We want to find the extreme values of the function over rectangular region D, x and y, such that x is bounded between 0 and 3 inclusive, y is bounded between 0 and 2 inclusive. When we say x is bounded between 0 and 1, we're talking about these two vertical lines and any region in between. And when we are talking about y bounded between 0 and 2, we are talking about these two horizontal lines and the region bounded between these two horizontal lines. So let us begin. First, we need to find the critical points. We are taking the derivative with respect to x, 2x minus 2y, set it equal to 0. The second equation, partial derivative of f with respect to y, which is negative 2x plus 2 equal to 0, but this is a system of equations that we consider. The second equation gives us negative 2x plus 2 equal to 0, so x becomes 1. When x is 1, plug that into the first equation, 2 times 1 minus 2y equal to 0, or 2y is equal to 2, or y is equal to 1. So we found the critical point, which is 1 and 1. Now, x is 1, y is 1, z becomes 1 as well. You have 1 squared minus 2 times 1 times 1 plus 2 times 1, which is 1. So let us highlight this. This is important. The very first z value that you found is equal to 1. Now, we look at the boundaries here. You have L1, L2, L3, and L4, which are all line segments. On L1, your y is equal to 0. So this is L1. As you can see, the y value, basic algebra, is equal to 0. So you can reduce the function. You can reduce the two variable function to a one variable function. F of x and 0 is x squared. This is a parabola, everybody. When you're working with a parabola, in this case, on interval 0 and 3, you can easily find the maximum and minimum value of this function. When x is equal to 0, f of 0 and 0 becomes 0, which is the minimum value of this parabola. When x is equal to 3, you get 9, which is the maximum value of this parabola. So far, we have 3 points. f1 and 1 is 1, f0 and 0 is 0, f3 and 0, which is 9. But this is just on L1. What about L2? On L2, x is equal to 3. So this is your L2. This is your second line segment. X is fixed and is equal to 3. So since x is equal to 3, your function reduced to a function in y. This is reduced to a one variable function, 9 minus 4y, which is just a line. This is a decreasing line. For this decreasing line, since the line is decreasing, it takes its maximum value at the beginning. So f of 3 and 0 is 9, and its minimum is at the endpoint f of 3 and 2. is equal to 9 minus 8, which is 1. So far we're done with L1 and L2. Let us move on to L3 and L4. Let me highlight these as well. So far our maximum value is 9, minimum value is 0. Very good. On L3, as you can see, your y value is fixed and it is equal to 2. And x is bounded between 0 and 3. You can reduce the function into x squared minus 4x plus 4, which is a parabola. The behavior of this parabola is very easy to work with and analyze. This function also can be written as x minus 2 to the second power. The minimum value of this function is f of 2 and 2, which is 0, and the maximum value is f of 0 and 2, which is 4. How? You're going back to elementary calculus. The derivative of this function, I'm just taking the derivative of this function, 2x minus 4. You can set it equal to 0. 2x is equal to 4. So x is equal to 2. And this is your critical point. This is just elementary calculus. When x is equal to 2, your y is also 2. You get 4 minus 8 plus 4. And this is f of, let me just correct this one here. So here you have your critical point. And since your y is also fixed, is equal to 2, f of 2 and 2 becomes 0. So here f of 2 and 2, which is 0 squared over 0. And the maximum value of the function, here you have 0 as the initial point. When you plug in 0 here, your function f becomes 4. So you found 2 more z values. Here we go, 0 and 4. From previous slide, the maximum value was 9, the minimum value was 0. Okay, so let us move on to last line segment, which is L4. On L4, your x is equal to 0, and your y is bounded between 0 and 2. And you can reduce the original function, two-variable function, to this increasing line. And this is just an increasing line. For this line, the maximum value of the function happens when y is exactly 2, which is 4. And the minimum value, if you plug in 0 for your y, you get 0 back. So comparing these values actually help us to find the maximum and minimum value of the function. The minimum value of the function on this closed rectangular shape is 9, and the minimum value is 0. So if somebody asks you what is the maximum is 9. And what is the minimum? The minimum is z equals to 0. So that's how we find and analyze the maximum minimum value of the function over enclosed regions.